This is going to be by far my most important video on electricity. I will show you a recipe to answer any A-level electricity question, and I will use it throughout the rest of my series. So before we get started, I need to give you one formula that we're going to be using, and that's the total resistance in series is RT is equal to the resistance of resistor 1 plus the resistance of resistor 2 plus the resistance of resistor 3. And I'm going to call that equation 8. Now let's look at a series circuit potential divider example question. Now I'm going to break this question down and do a really detailed step-by-step recipe. In the following example, I'll then go through exactly how I'd answer this in an exam. So let's read the question. It says, explain what will happen to the potential difference across R2 if the resistance of R1 is increased. So you can see we've got a variable resistor and a fixed resistor. Now for any A-level electricity question, the first thing you need to do is write out what do we know. So what do we know? Okay, so what I mean by this is, well, we've got a series circuit, so I'm going to write out my series circuit rule. So in series, I know the total current is equal to the current in resistor 1 and is equal to the current in resistor 2. That's the equation from an earlier video. So the current in each component is the same as the total current. But potential difference is split proportionally. So the total potential difference is V1 plus V2, i.e. the potential difference across resistor 1 plus the potential difference across resistor 2. This was equation 3 from earlier, and this was equation 4 from my notes. Next, we need to recall what Ohm's law is. And it's a really important point that you can apply Ohm's law to the total circuit and to each individual resistor. So what I mean by that is we have Ohm's law for the total, so VT equals IT RT. Ohm's law applied to resistor 1, V1 equals I1 R1. And V2 equals I2 R2. We've just said that current is the same in a series circuit, which means IT is the same as I1 is the same as I2. So let's go around now and change this to IT. So V1 equals IT R1, V2 equals IT R2. That's going to come in handy later on. Now I'm going to go into step 1 of my recipe. So step 1 is we need to look at the total resistance. And remember, equation 8 from the start of the video in series says that the total resistance is R1 plus R2. Then we look at the question and it says the resistance of R1 is increased. So R1 increases. Now we know that R2 is a fixed resistor by its circuit symbol. So we say R2 is constant. Okay, so if R2 doesn't change and R1 increases, then RT must increase. So we're going to highlight that and use it later on. Next step in my recipe is to look at the total current. Okay, now recall the formula for Ohm's law is VT equals IT RT. So total current is total potential difference divided by total resistance. Now the total potential difference is just supplied by the cell, and that's constant. So I'm just going to write VT const, and RT we just found, RT increases. Okay, so if this stays the same and RT increases, then IT must decrease. The denominator of the fractions got bigger, so the whole fractions got smaller. IT decreases. Now, the next step in my recipe is to look at any fixed resistors. So step 3, is fixed resistors. So I'm going to scroll up. R2 is clearly the fixed resistor, R1 is variable. So I'm going to look at V2 is IT because current's constant in a series circuit, R2. We've just found out that IT decreases and R2 is constant because it's a fixed resistor. So if IT decreases, R2 is constant, then V2 must also decrease. So V2 decreases. So let's look back at the question. We found that if you increase the resistance of R1, then the potential difference across R2 will decrease. Now, the next step, or the next part of my recipe, is we want to look at the total potential difference. And this says, in series, total PD is potential difference across component 1 plus potential difference across component 2. Okay? We know that the potential difference supplied by the battery, VT, is constant because it's just a cell. So I can say VT is constant. V2 decreases. So if this stays the same and V2 decreases, we need V1 to offset that decrease in V2 so that this doesn't change. So that means V1 increases. So we found out what happens to the potential difference if we increase a resistance. Now it's really important to remember these steps in the recipe. So step 1 was total resistance. Step 2 was total current. Step 3 was fixed resistors. Step 4 was total PD. So if you use this recipe, you'll be able to answer any potential divider circuit question. Now let's see how this comes up in an exam. If you're feeling confident, pause the video and have a go. If not, my next video, I'll go through plenty more examples, so there'll be plenty more opportunities for you to have a go. Let's read the question. The diagram shows a potential divider circuit that contains a negative temperature coefficient thermistor. Now we haven't covered these yet, but this just means if the temperature increases, the resistance decreases. That's just a fact you need to remember for now. Then it says, the temperature of the room containing the circuit increases. So that tells me that the resistance of X decreases. Okay, so that's going to be important for now. Select the row of the table that correctly shows the changes in readings on the meters. So we want to find the potential difference across X, the potential difference across Y, and the total current in the circuit. Now let's use my recipe. Step 1 in the recipe was total resistance. Now, total resistance is RT equals the resistance of X plus the resistance of Y. We can clearly see RY is a fixed resistor, so that's constant. And we know that Rx decreases because it's a negative temperature coefficient thermistor. So, Rx decreases, Ry stays the same, RT decreases. Step 2, total current. IT equals VT divided by RT. VT is constant because the total potential difference, or the EMF, isn't changing. We just found out that RT decreases. So this stays the same. RT decreases and it's on the denominator. So total current increases. So it implies IT increases. Okay, that's really good because now I can see total current must increase. So I know it has to be B or D. Now the next step in my recipe was to look at any fixed resistors. So step 3, fixed resistors. Vy is clearly fixed. So Vy equals It, because current's the same in series, Ry. Ry is fixed, so we'll say it's constant. It, we just found out, increases. So this stays the same. It increases, so Vy must also increase. So Vy increases. Now let's look at our table. We know that Vy increases. So we know the answer is going to be B. But let's just double check because we haven't worked out Vx. I could have made a mistake, so I'm going to double check. Let's go on to step 4. Total potential difference. Okay, I know that Vt equals Vx plus Vy. I know that Vt is constant because it's just the cell and we haven't changed the cell. Vy has increased, so this doesn't change. Vy increases, so Vx must decrease to offset the increase in y. So we can say that Vx decreases. And there we go. It aligns perfectly with B. So the answer is B. Now, if you found this video useful and you'd like the lesson notes and a full question pack to go along with it, please visit my website. I've left a link in the comment section below.